Hello all, my name is Balint Hodossy, and I'm a second-year PhD student at Imperial College London and part of the CDT in Prosthetics and Orthotics. This presentation is a summary of my work so far in the topic of walking motion prediction, titled Neural-Driven Gait Synthesis with Temporal Convolutional Networks. Developing devices that support and restore mobility is an increasingly important objective due to the projected demographic shift towards an aging population. However, for people whose gait is affected by age-correlated conditions such as spinal cord injury, stroke, or Parkinson's, energetically passive prosthetics and orthotics often cannot facilitate activities of daily living such as climbing stairs or walking independently. Actuated devices like exoskeletons aim to address this need by assisting ambulation with associated benefits to cardiovascular and musculoskeletal health. Thanks to developments in actuation, energy storage, and sensor technologies, these devices are approaching the required biomechanical outputs in terms of power, speed, and versatility to support the mobility of their users. In order to take advantage of this progress, new control strategies are needed to synchronize the generated movement with the user's motor intent. Existing control methods for commercial exoskeletons mainly consist of manually selected activity modes, predetermined movements along straight paths, and turning in place. While this can be sufficient for rehabilitation therapy in a controlled environment, it is not suited for locomotion in everyday scenarios. Early user reactions suggest certain user expectations need to be met by the control strategy to mitigate the high abandonment ratio associated with mobility aids. These include requirements for intuitive and inconspicuous walking at convenient speeds. Therefore, responsive, voluntary control interfaces that produce stable and efficient walking need to be established. I'm investigating electromyography or EMG-based motion synthesizers, as these signals have a natural connection with motor control and hold information about the upcoming intended movement even before it begins. A further goal is to see if neural network-based EMG control models that have already seen success in the upper limb control context have useful applications to locomotion. Lastly, I'm also exploring whether or not techniques and methods from the related field of interactive character animation have important lessons for P&O device control. While EMG is a promising input modality, many potential users who could benefit from exoskeletons, for example, spinal cord injury or stroke patients, have compromised signal quality in their legs. In these cases, EMG could be sampled from other areas correlated with walking, for example, the trunk. Furthermore, due to practical and safety considerations, signal acquisition is a lot more convenient with surface EMG and with limited number of channels. A possible way to make stable predictions from these noisy inputs is to extract the necessary information from the temporal context of the signals. Traditionally, in deep learning, recurrent models are used for this. However, temporal convolutional networks have recently been shown to perform comparably despite requiring a lot less data and time to train, as well as being easier to construct. The first approach I took was predicting joint angles directly from EMG. For this reason, I collected motion capture of the lower limb to extract the joint angles in the sagittal plane of the hip, knee, and ankle, and concurrently I recorded 8 channels of bipolar EMG on the trunk. Since ambulation is a tightly coupled and autocorrelated process, there is a lot of information in the past samples that we can use to predict the current one. Due to this reason, for any single target angle value, I use a window of preceding EMG values from all channels to base the regression on. This can be represented as a sliding window that holds a frame of normalized EMG data paired with the target angle in the one-step ahead prediction setup. These windows are the input to the temporal convolutional network. In the feature extraction phase of the model, a set of adaptive one-dimensional filters extract temporal patterns from the muscle signals. In my experience, it is important to don't mix the information from the channels immediately and instead use channel-wise separate filters with features unique for each muscle. The increase in dimensionality caused by the convolution is balanced with pooling layers. These reduce the complexity along the time axis by keeping only the most relevant samples. This is then repeated with a set of dilated filters, which extract secondary features in a wide field of view. After these features are extracted, they are flattened into one long vector, which is then fed into a densely connected network, making the actual inference. At the end, it's making a prediction of the 6 desired joint angles, and the errors between the prediction and the actual angles as determined by the motion capture are calculated and backpropagated all the way to the start, making updates along the way. I've collected this data for 5 different non-P&O user participants and trained models specific for each user and specific for tasks like walking, sitting, and stair climbing. Within these constraints, the performance of the trained networks were comparable to prediction systems that use EMG from the leg instead of the trunk, or many channels with high-density electrodes. These results suggest that the temporal context of trunk muscle signals hold a lot of useful information about the gait phase. However, since this model estimates the intended joint kinematics directly, even small errors and biases can be magnified along the kinematic chain of the lower limb, leading to unsafe and unstable movement. Furthermore, there is no straightforward way to transition between activity modes or to modulate the gait according to high-level objectives such as turning at different angles. There are further drawbacks of control strategies that map muscle signals directly to kinematics. A monolithic model like that is hard to debug and analyze. Changing a parameter to influence the way it processes the incoming signals will have side effects on the synthesized motion and requires retraining of the entire system. Therefore, a lot can be gained from separating the model into hierarchical layers that interface between each other. Then, each layer in the control flow can be tested, evaluated, and iterated upon separately. Furthermore, this adds to the modularity of the control strategy, since subsystems with common interfaces can be swapped out. High-level control corresponds to the abstract intent that underlies the motion. In a gait context, a possible representation that I've chosen is the future walking path trajectory. Based on this intent, a desired walking motion can be synthesized by the mid-level controller. Finally, the low-level controller actuates the different degrees of freedom with physical limitations in order to reach this kinematic state as close as possible while maintaining goals such as balance and smooth movement. So far, I primarily investigated high and mid-level control options. I re-implemented a motion synthesis technique from the animation industry called motion matching, which would be controlled by a human-machine interface-derived estimation of the intended horizontal trajectory. This recording shows gait synthesized by motion matching. The red line is the target trajectory, currently determined by an input from a conventional joystick interface, which would be later replaced by a prediction that's based on human-machine interface signals. Motion matching periodically searches its database and blends together segments of previously seen movements to follow the desired input. The currently playing clip's index and the time inside the clip is shown in the top left corner. The white line shows the generated actual past trajectory. Similar to the model predicting joint kinematics directly, I aim to collect a dataset of EMG concurrent with motion capture. Once the horizontal walking trajectory is extracted for each frame in the dataset, the prediction model can be trained to estimate it from a window of muscle signals. This low-dimensional description of intent can be interpreted and effectively decompressed by the mid-level controller to generate realistic and safe walking. So this video shows an example from a proof-of-concept dataset I collected with one subject. On the right, you see the desired outcome variable, which is a 1 second long window of future horizontal walking trajectory. Different turns and at different angles were performed by the subject. And on the left, you see a window of 8 channels of EMG that we are trying to use to predict the trajectory. Current early models that operate on a half-second delay can predict not only the onset of motion, but also the turning direction, and make a reasonable guess of turning angle as well. There are some key limitations to consider in a deep learning model like this, or like the ones discussed earlier. Since the dataset consists of a single participant with a single recording session, the model is expected to overfit to the participant's signal characteristics and the specific electrode configuration used. Therefore, it is important to expand the dataset in the future with more participants and electrode refittings. A further limitation is that the network can't synthesize trajectories that are too different from what it has seen. In this example, there was only one recording where the participant took a few steps backwards. When this recording was not in its training set, the trained network misinterpreted that section as moving forward. Furthermore, when exploring models that predict without a delay causally, there is a significant drop in accuracy so far, especially in predicting turning direction. This shows that while EMG has reliable information about the phase of the gait, it is more challenging to use it to discern high-level gait patterns, such as turning. The previously described motion matching system can use these predictions to synthesize the entire walking trajectory. However, even when predicting with the ground truth, there is some loss of information. When using trajectories that have been predicted from the EMG as opposed to the ground truth, we can see that even more information is lost. Although the angles are inaccurate, the actual turning direction is retained. The actual relevance of all this, the exoskeleton control, is that this synthesized motion could then be used as targets for a low-level controller that actuates a device like an exoskeleton. A separate layer of low-level control would be needed to actually try to track these target motions within physical limitations. And this would complete the 3-level hierarchical control strategy proposed. A good candidate method to produce low-level commands would be reinforcement learning. Reinforcement learning agents have been shown to produce movement that is robust to perturbations and physical limitations, such as maximum torques in joints in simulations. In my project, I would like to partially validate my control systems in similar virtual environments. I also intend to further explore different intent estimator variants, such as by introducing recurrent elements. I plan to investigate different input modalities, such as IMU or foot contact data, as these signals hold important information about gait as well. As discussed earlier, the limitations of the deep learning aspect of the model would need to be addressed. I'm considering how to perform user-in-the-loop online testing for validation of different subsystems. To de-emphasize deep learning, I'm investigating how to involve conventional, fully voluntary control interfaces, for example, signals derived from head orientation. I would like to thank you very much for your attention. If I miss you in the conference, feel free to get in touch in the email if you have any questions.